So wonderful. Good afternoon, dear LinkedIn community, on this nice Friday just before the summer holidays. Our discussion today will revolve around, but not only around, including crashing of composites. And my guest today will be Tim Hall. He's a commercial director of Engenuity. Welcome to my show, Tim.
Hi, okay, nice to see you.
Wonderful. So let's dive into Ingenuity first, the company you are working with, where you are the commercial director. Tell us about Ingenuity and then specifically your role at Ingenuity.
Sure. So Engenuity is an engineering services company. We were set up around 30 years ago in the realm of structural engineering and particularly CAE, computer-aided engineering. Back 30 years ago, so we're talking 1993, there wasn't a huge market in computer-aided engineering. It was kind of in its infancy, and in particular, in composites CAE, there was near enough nothing. It was very limited, the capabilities. So actually, Engenuity as a company set up one of the first ways that we could include composites in the CAE arena, with a program called the Laminate Modeler, which was licensed to Patran, written by Engenuity. And since then, we've spent 30 years staying at the forefront of that industry of capability in composite CAE. Really, we have an ethos as a company that if you can make accurate predictions through computer models and through computer material models, then you can create better structures. And that's what we aim to do. And we're quite unique that we have that focus on both materials and analysis under one roof, and such a strong connection between the two. But that allows us to do a lot more virtual development and get our customers better products and faster, and using this more predictive capability. Now we're part of the HRC group, which is a composite mass manufacturer in China, and we operate as their engineering arm. So we joined HRC, the HRC family, in 2018, and really the aim was to bring this advanced engineering capability to the Chinese market, where they've been very successful.
That's a great introduction. Thank you so much, Tim. And now is the time to welcome our guests here in the LinkedIn Live. Sorry. So welcome to our LinkedIn Live, dear guests. By the time we've gone live now, there's a small time lag here in between our discussions and your chat. Please write in the chat from where you're tuning in today. Are you from the composites arena? Are you applying composites, or what is your interest in composites? We would like to know about that. And meanwhile, Tim, can you explain us what sort of industries are you specialized in? The reason I'm asking is CAE, computer-aided engineering, for those who have not heard about that term before, is, of course, a very wide field and can be applied in many, many sectors and many industries. Also, composites, as being a lightweight product. It can be lightweight, but it can also display different other features like very strong material, corrosion-resistant materials. So are there any specific markets that you have Ingenuity focused on yourself, or can anyone approach you with, a CAE or crash design?
Yeah, so because we're so structurally focused, I say we specialize in structures rather than specializing in an industry. When we first started, we actually had a lot of work at the time from aerospace, and we did a lot of aerospace projects, and also that changed after a while, and we did more automotive. Automotive, I would say, is still over 50% of our business. In the early days, we did Le Mans a lot, so we were the structural development behind a lot of winning Le Mans chassis, a lot of Le Mans cars from that era, and we've taken that approach of that if you understand your material and you use the right analysis techniques, then you can really apply it to any structure in any industry. So throughout automotive, we work with Formula One now, Le Mans, and have done for decades. We work in road cars. We have published works with the likes of BMW. We work a lot on motorbikes, and a lot in the hypercar, supercar arena, as well as everyday road cars. So automotive is quite a broad range of offerings there, but we also still do aerospace, and there's a really exciting new industry growing at the moment in eVTOL or urban air mobility, this sort of market of electric flying cars, or however you describe them, where there is a big weight challenge there, and there's not many places you can reduce weight from. You know, the battery weight is pretty much fixed, so are the motors, so are the passengers. You can only really take the weight out of the structure, and that's where our skills really come into use. Just generally structural engineering, as well as a potential crash regulation there in the future. We also work in marine, mainly on the racing side in marine. As a company, it's really quite broad. We even do heavy industry projects, you know, medical industry as well. So we have a wide variety, but always, yeah, structural engineering is our focus.
There are so many threads that you gave to me now, where I can, you know, ask hundreds of thousands of questions, but we need to focus, of course. But let me ask one thing, because that caught my personal attention now. You say medical. Where are medicals so important? Can you give me a concrete example about on which medical device you have been working on lately? Of course, without giving names and things like that.
Yeah, so we're doing some fatigue development in sort of larger machines. So where say you're using imaging, or you're trying to use radiation to treat cancer, for example. These are examples where you need strong structural stability in the machine, but that machine is also quite heavy. It might have shielding in it, or the generators of the radiation is quite heavy, complex equipment, and you need to maintain that stability over life. And so we can bring that capability, that engineering capability, to the medical industry, which is quite interesting for them. Particularly if you say, you know, you're treating a cancer with radiation, the more accurate you can make that, the better the side effects for the patient, the less healthy tissue that you damage while you're treating them. So there's you know, a number of benefits that you get from just good structural engineering that we can bring.
Very interesting, very interesting. So you've mentioned flying cars. We have been at JEC this year in April 25th to 27th, and we have seen the Xpeng, the flying car. That was a fantastic part, and I assume you, if I remember rightly, the HRC group, and I'm sure you have been involved in the simulation, had over 400 parts in that flying car. That was an interesting and a really exciting one. Actually, your picture on our thumbnail of this video thumbnail is in front of that Xpeng flying car, right?
Yeah, the X2 project was a really exciting one for the HRC group, and there are I can't remember the exact numbers, but I think it's over 100 composite parts on that. A number of different processes that were developed and really done in a really short time frame. I think from start to finish, it was just a matter of months to get them the flying prototypes. They can really start to learn about it. Generally, in the industry, yeah, there's you know, there's a lot of players now in that industry, and I guess they're quite an innovative bunch. I would say that there are people there who are looking for solutions that possibly the traditional aerospace manufacturers wouldn't consider. And they've got good reasons for looking at new solutions. As I mentioned before, weight is a huge challenge, and really that weight has to come out of the structure. And they had the sort of crash requirements. There haven't really been published regulations yet that we've seen in terms of crash, but we think that there might be possibly more stringent regulations for those, more akin to a helicopter than it is to a big trunk liner. So yeah, that's interesting. Again, things like the everyday loadings of the aircraft as you try to maneuver as you land, hard landing. How do you make sure all your systems and your passengers are comfortable and everything keeps working time and again? The other problem they have is on production rate, that some of these companies are quoting to make 1,000 or 2,000 of these vehicles a year, and that's a very different production rate to what we see in traditional aerospace. And so they're looking at new manufacturing technologies, and even looking at randomized short fiber, which is something I think we'll talk about a bit later on. But we have some interesting projects going on there, including one with Spirit Aerosystems.
Yes, exactly. In the X2 project, you had also this SMC carbon interior parts that also caught my attention, and we will talk about it. And before we talk about composites crashing now in detail, let me ask you one more thing before we come to crash analysis. So how do customers typically benefit from your services?
Yeah, so I guess if you compare a couple of different potential routes, and there's, for thousands of years, humans have had this idea that when developing technology, we'll make a prototype and see how it behaves. And we can do so much better than that now. And CAE's allowed us to do this virtual prototyping. The Engenuity ethos is around to make a structure work perfectly. There are a few things you have to consider. And one are the loads that structure has to take. So that could be in terms of physical loads and stresses and things it has to carry, or in terms of what temperatures it has to operate at, or what chemical environments it operates in. So that's the loads. Secondly is the material, and what you really want to understand is what the material is capable of. In metals, people who come from metals, they often just look up the data sheet online, and all the alloys come with a nice certificate saying it passes, and that's easy. Composites are so inherently tunable that you can change so much about the composite, but you have this rule of unintended consequences where you might tune the composite to achieve one thing and it makes it weaker at something else. So we have this recommendation at Engenuity that we always should be measuring the composites we're designing with. And the third one is the geometry and how we develop the geometry and the latest techniques. So we have a lot of commercial software in-house, but also our own techniques that we use for things like crash analysis, and another new technique for SMC that are quite unique, but it's just using the right tool for the right job. So in terms of benefits, I mean, these services, really customers pick and choose which services they want from us in those different areas. For an OEM, it's having that expertise in a CAE company that they can come to and understands, talks their language, whether it is hypercar, supercar, motorsport, a boat, a plane, or anything. We can support them in their development, either just having that solve a problem that they can't solve, or just be capacity expansion so that they can keep their projects on track and have enough engineers to deal with them.
Motorsport is a really interesting field. I had the joy to talk to a Formula One driver just the other day in Bologna at JEC Forum, Italy. Jarno Trulli. He was a very famous Formula One driver in my youth, and I spoke with him about composites and materials, and he was very, very knowledgeable. Do you have contacts to Formula One and Formula One drivers at all?
I guess we don't talk to the drivers so much, but the technical teams, the structural engineering teams, yes, and multiple teams use our software and our characterization services, because we have some really nice capabilities we've developed, and yeah.
Silverstone is quite a bit of a distance to Burgess Hill, right?
Yeah, maybe 3 hours. It's not impossible.
It's near to the place where the International Composite Summit will be in Milton Keynes, right?
Yes, it's just down the road actually from Milton Keynes, and you have Milton Keynes obviously famous for the Red Bull racing team that are based there.
Oh, very good. Okay, so maybe we have a chat with Hamilton then when we meet in the UK. So let's come to crashing, because I'm seeing right now we have really a bunch of nice number of viewers. To all our viewers right now, this is a LinkedIn Live with a LinkedIn Live interaction. So there is a function down below, which is a chat. Please write down in the chat from where you are tuning in and what composites are you working with, or are you here just for out of general interest? Let us know and write in the comments, because we would like to see the reach of this LinkedIn Live, and we would like to get to know you guys, of course, because if you don't react, we have no clue who you are. And by the way, thank you for the comments so far. I will attend to those comments within a moment, but let's talk now about crash analysis, crash simulation. Tim, what have you brought for us on crash simulation? Explain to us, why is crash simulation so important?
So yeah, I guess there's a lot of structures, particularly in vehicle engineering, and you know, a structure, you're engineering it for the worst possible load cases. You know, there's going to be some situation that's going to be some things are easy to pass and some things are difficult, and crash is often one of the difficult ones. If you could do your crash development virtually, it saves you a huge amount of money, because you're not making vehicles, breaking them and trying to understand what happened. And CAE is an excellent tool for this. You know, you have a number of different, a crash can almost be thought of as a number of different failures going on all at the same time. And traditionally, the explicit modeling software that people use globally is very good in metals at predicting the sort of failures that the metals go through. They you know, they bend, they buckle, they fail in tension, compression. All these different failure modes are quite well understood, and they can do those failure modes as well in composite. But in composite is excellent for crash absorption, because it has a very particular failure mode, which we at Engenuity call crush. I have a video on that actually. We could quickly show, but crush is so this shows that crush failure mode. You just play it again. Thanks, Ilkay. Yeah, it shows that the composite material, it fragments into lots of tiny pieces, and as it does that, it absorbs all the energy of the crash. And you can see in that video that big heavy impactor, this video is obviously heavily slowed down, that has kinetic energy as it's traveling, and that crush, turning that kinetic energy into those tiny fragments of composite, it's absorbed all the energy and it's protected everything that's behind it. And when Engenuity started doing crash back in the Le Mans days and for other projects, we used to actually do this crush by hand, because we couldn't find a way of doing it in the CAE. So in the end, we developed it, and we developed our software called C-Zone, which is a add-on to explicit engineering software programs that can handle this crush failure mode. And once you start to separate out crush, you can actually measure it in the lab. There's so we now have that predictive capability. We can look at what materials are good for it. So we can look at all of that in the lab, and then you can do this virtual development. So if you know, we've heard about companies just doing lots of prototyping. Sometimes people prototype to try and correlate their models, but even up to monocoque size things that they crash, and between one company was building between 5 and 10 monocoques to crash it, to try and correlate their models so they could predict what was going to happen, and it just sounds completely backwards. They wouldn't do that for strength, they wouldn't do that for stiffness. They can just trust the computer models on that, and so C-Zone allows you to trust the computer models for crash as well. And the costs and the time of building 8 to 10 monocoques to then break them, you know, you might be talking €1 million or something of that order, and the time, you know, over a year. Whereas in a few months, we can develop and simulate 20 or 30 or 50 designs of potential ways that you could do all your packaging, you can have all your crash set up, and you can make it work first time. And actually, we have customers who have done exactly that they were building Formula One nose cones, and they would make 10 of them because they didn't know what was going to pass and what was going to be the lightest, and now they just need to build one because they can use our software. So it's very much shows Engenuity's capabilities in one of the most extreme cases, to be able to use the materials together, materials testing together with the analysis, and having that strong link to be able to do the virtual development of crash and be confident that you're going to be able to pass those tests when you get to them. I have another video actually that shows a vehicle. This was a road car setup, and it was actually a project with BMW that they've posted online, and we're allowed to talk about. So we worked with BMW to help them set up and look at the way they were doing composite crash, and I guess through the project, this is one of the first. They were learning the process from us as it goes through, and this is one of the first simulations that together we set up and did a validation test. So you can see the validation test on the left, and the one on the right is a pure prediction of what would happen in that test. This is a black metal design. This isn't something that's been optimized for composite, but it has a number of composite parts in that CZone is working on, and they were very happy with the results that they could do it. Really, I think the rule was that if it can't be simulated, it won't go on the vehicle, and so that opens up the market to more composite crash. And as I said, composites are an excellent material for energy absorbing. Not only are they lighter than say an aluminium crash cone, but they're also smaller, because when you crash an aluminium cone, you can really only use 2/3 of the length before the aluminium becomes so rigid it just transfers the load rather than absorbing it. And composite, you can use the whole length for that crash. What CZone also does really nicely is, although you are using it to analyze the crush, every other failure mode that's in your explicit analysis package is still there. So when you load up that crash cone and you're trying to absorb that energy, that there's going to be a force that's then transferred to your monocoque, or whatever else is behind it. We call that area the backup structure, and CZone also predicts everything that's going on in the backup structure. And some of the alternative techniques we've seen, when you get the force output from the forces transferred to the backup structure, they're very peaky. They have some extremely high forces and some very low forces. And on average, they might be about right. But if you predict that there's going to be a very high force that's going to be transferred to your backup structure, then your tendency is to over-engineer that backup structure to take that very high force, which is that force isn't true. It's just that the software simulation can't handle what's really going on in that crush failure mode. And so compared to that, you can then get you can do the development virtually. So you've got not only a faster result, a cheaper result, because you haven't had to build all those parts and break them, but you've also now got a better result. You've got a lighter weight structure, both in your crash structure and your backup structure.
Okay. Tim, thanks for your explanations there. Now we are approaching roughly half time, dear community. So this is a LinkedIn Live that is supposed to go from 1 p.m. to 2 p.m. Central European time, or in British Standard or summertime, it is from 12 to 1 p.m. And I would like to take the opportunity, Tim, if you allow, to greet our guests here. We have Nedim from Turkey. He says, hello. Thanks, Nedim, for your loyalty, always watching our LinkedIn Lives and my posts. Santosh, I guess he's from India. Thank you, Santosh, for joining our show today. I understand you have also a lot of experience in composite structures. So please keep on commenting on what Tim is telling us today. Then we have Voigt Composites in Garching from Germany. Wonderful. Burla is there today. His profile seems to be on private modus right now, so we can't see his picture. Andreas Horbach says hello. Yes, Andreas, hi, nice to see you. From where are you? Please write it down. And if you are interested in composites, let us know what is your concern with composites. And then Anna Gregory Hall says she's from Reading in the UK and generally interested in composites. Really interesting to hear about the flying cars. Anna, this is wonderful. Reading is also near London, isn't it? Or somewhere in between Milton Keynes and Burgess Hill, right?
It's it's about 50 kilometers west of London.
Okay, so we are back in the UK. So any questions, please write them down. Then we got Martin, and he puts, of course, the right emojis there. Amin says he's a PhD. He's working on honeycomb panels with viscoelastic foams core inside the holes, and he managed to release a study which isn't published yet. It enhances the crash behavior in thin-walled structures by adding value to the dissipated energy due to the crash. Now, we will be having this show on a podcast soon, and that is the reason why I'm reading your comments, dear community. And for our podcast guests, hello by this time. And Amine, before we come to the next question, do you have any experience with honeycombs? I bet you do.
Yeah, they do interesting things in crash. I'd be really interested to see this research and understand.
Okay, Amine, so reach out to Tim, and you guys have a chat. Then we got a LinkedIn user also on private mode from TPI Turkey. TPI, we know TPI all from the wind industry. Let me just check on my mobile phone. It's Sema. Sema, hi. Nice to see you in our show, and I hope you will get a lot of takeaways from Tim and myself today. And then Amin says, Ilkay, it's all about structural engineering in composites parts. Here we go. We have reached our target audience, and I hope you guys see a lot of benefit watching us today. I'm talking with Tim Hill. He's the commercial director of Engenuity, which is part of the HRC group. And they have subsidiaries in the UK, in Spain, here in Germany, obviously. In Germany, the Director of Business Development is Erich Fries. I hope Erich will be seeing this also soon in the replay. Erich, my greetings to you at this time. Then Martin says, very interesting what happens to the honeycomb. I guess that's the question that he asks Amine Harkati. Then we got Balázs from Hungary. Yes, Balázs, nice to meet you again. Hope to see you soon again at the next Jack in Paris. Then we have Amine is answering Martin based on Hashim damage criteria. The viscoelastic damping delivered by the foams increase the dissipation of the energy consumption. I can imagine that. Yeah, it's a good explanation. Any ideas from your side or anything you want to
add? From me, yeah, it all depends on the properties of the foam. Some of them just, yeah, they don't tend to shrink down to zero space, so they will absorb some energy, and then it's what that foam does as it builds up, and how does it particularly if it's a sandwich structure, how it might then break through to the skins and then cause you problems because it's sort of just pulling your crash structure apart. So yeah, there's as always in composites, it depends on so many different factors, and it's good to be able to get these things in the lab and really see what's going on and the best way to use it.
Absolutely. Yeah, there are so many different kinds of these foams, and I'm sure Amine has checked all the kinds of foams. I myself, I'm not a foam guy, so I have nothing to add on this one at all. I'm from the textile industry, the reinforcement side. I'm even not chemist. I'm from the fiber side. And even with the fibers, you got so many choices like E-glass fibers, R-glass fibers, AR fibers, silicium dioxide fibers, silica fibers, ceramic fibers. The list goes on and on and on. Then we go into aramids, meta-aramid, para-aramid, carbon fibers. And in each one, of course, has a much different behavior in crash simulations, heat simulations, and chemical situations, for example. And then Balázs says, here's a question, I guess. We have experience about crash analysis of hydrogen pressure vessels in trucks or passenger cars. Good one, because hydrogen, of course, is the hot topic these days, right?
Yeah, so we're doing a lot of work in hydrogen. I don't think we've looked at them in the crash situation, but they're no different from any of the other systems that you might be putting in the vehicle. You've got to understand what's going to cause them to fail in terms of impact and how you can make your structure better suited to avoid that. So for sure, what we've been talking about dissipating energy, and also, particularly I imagine for a hydrogen tank, you want to avoid having some sharp cornered piece that pierces through the tank and causes that release. So there's a number of things to consider. I think we've done both halves of it in terms of the crash analysis and of looking at failure of hydrogen tanks, but I'm not sure we've ever put them both together. So another interesting topic brought up there.
So thank you guys for all your questions and your comments. I really, truly appreciate that. Tim and we are always happy to answer all your questions. So please keep on answering and keep on asking your questions. We will come back to all your questions later on. Tim, let me come back to one of the things that comes to my mind oftentimes is, can you quickly walk us through when would you use CAE, computer aided engineering, for simulation, and when would you need to make a physical mock-up in order to find the behaviors of composites? Do you have a guideline for this, or would you say CAE can replace everything?
I wouldn't go that far. I would say that CAE is a helpful guide right from the start of the project. That when you start producing concepts and you start to figure out what your product is going to look like, what your structure is going to look like, it's so easy now. You can put that into a model, and you can start to understand the sort of properties you're going to get out of that structure and any particular weak points. And CAE, as I said, it's accessible now, and it helps to have some experts on hand to as you start going through that process, as you start developing designs, to be using CAE right from the very start. At the beginning, probably it's just sort of a concept analysis. You're not worried too much about the exact properties. You just want to use some representative properties, and even you don't need to look at too much about the failures and how you're going to avoid them. Just to know that this area is going to be a problem. How can we reconfigure the structure to make it more reliable? So I'd say right through it, validating the models is always useful. It's just an extra check, really. So prototypes aren't going to disappear, but I hate to see people doing development through prototypes through multiple tests when you probably just need one to validate the model.
Yeah, so it's really a cost-effective way to take, to answer some basic questions and to get the model confirmed in order to really save cost. And like you said, rather than doing multiple prototypes and eliminating one failure after the other, is better to simulate those on a computer and then do the right and true testing.
Yeah, that's right. Another way is to use prototypes and CAE together, is to think about, you have to tell the CAE what loads the part's going to go under. You might not fully understand that. So to make a prototype, you can then possibly do slightly more thorough testing with it. You could do say a vehicle level test, and then actually you find out that the models you put in, the loads you put into the CAE are incorrect. So it's nothing the computer's done wrong. It just helps you to let's revisit the CAE and let's try to quantify those loads that we didn't consider before. So yeah, so there's still use to prototyping, but it's just finding that right balance, and we think that it should be more towards virtual engineering.
All right, so I changed our ticker down below, and now it reads short fiber analysis. That's our next point. So we are wrapping up crash analysis here, dear guests, and let's talk about short fiber analysis. Why is it so important to check short fibers, Tim?
Yeah, so I guess what we're looking at really is say carbon fiber SMC, these types of materials, that they're much cheaper than continuous fiber, but they're not they're not used so much in structural applications, and I don't think they're fully understood the best places to use them. And what we see with when you have this randomized fiber, if you have a nice thick structure, then fine, all the fiber orientations essentially cancel out, and you have essentially a 2D isotropic material that you can design with quite easily. But if you're using a carbon fiber SMC and you're now probably moving into carbon fiber areas where you're trying to make thin structures, you're trying to make them efficient and lightweight. But with the short fibers, what we find is the thinner you go, the more you start to see the random orientation of the fibers start to cause you issues. And really, it's just a question of variability that you can say, I have a material property and I can apply it to my model. But if you actually make a number of parts, say you made 100 parts, you'd actually find that they all behave slightly differently. And when you're making thin, lightweight structures, and particularly if they're safety critical, you really want to be able to predict that variation. And that's what Engenuity has been working on with a software we have called FIRMA, or Failure in Random Material Architectures. And I guess the issue here is when you're talking about short fiber is that question of scale. As I said, thick is good. Thin, we know we have this randomization. We get a lot of variation due to the fiber orientations. And it's as you start to change that, you change what that variation is. There's no use just measuring one coupon and saying, well, I have a certain amount of variation, I can apply it to everything. Because as you change the geometry, you get this scale dependence on the performance. And I have an image actually I can show that demonstrates that. So on this graph here, we've got 5 different coupons that we've tested. So you've got long and thin, short and fat, and we've tested 3 of them up there in the tension region and 2 of them down there in the compression region. And the black dots are the test results. So you can see that there's a variation there, quite a considerable variation of that material, but also that pattern changes depending on the size. These are all quite thin coupons because that helps us exaggerate the effect of the randomization, which is something we're trying to do here. Because what we really want to do with FIRMA is to be able to measure the dependency on the scale and then use that to predict. So the colored dots are actually us. We've fed this data into our FIRMA software and asked FIRMA, how would these coupons behave? And it's produced the colored dots. So you can actually see that FIRMA's not just predicting the right sort of loads and stiffnesses that these coupons should be able to handle, but it's also getting the variation right, the pattern of that variation. And that's so we're at a stage now where we think we've got FIRMA to a place where it's scale insensitive. And this isn't just some clever AI saying I can put dots in the same place as those dots. This is following a physical model of FIRMA is randomizing the fiber orientations and applying a single material card. Essentially, it's applying it to the ply. So we have quite an advanced failure model that covers 0 and 90-degree directions of that ply that it can randomize throughout the structure. And you can see here that the predictions it gets on these simple coupons is very good. So taking this to the next stage, we've been working with a number of partners, including Spirit Aerosystems, to apply this in the aerospace industry. So as I mentioned, through eVTOL at the moment, there's a big problem in production rate with these aircraft, and so they're looking at SMC. But this variation is not good for aerospace. So we're hoping that if we can show people that it is actually predictable and manageable through simulation, then it will be a useful material, and we can start to see this more use of carbon fiber SMC in structural critical applications. What we're doing in this project is we've got a part of an eVTOL that we're going to redesign in SMC, and we're going to make some parts, and we're going to really validate this on quite a complex component that has even not just randomization of the fiber, but this new development will bring in the flow effects during compression molding as well. So we're going to have compression molded parts, which the compression molding is going to be simulated by our partners in Germany called Simutens, and then we're going to feed that into the project and into FIRMA to bias those fiber orientations.
All right. Tim, we got a question from Juan Pablo. He asks whether you can predict the fiber orientation in CSMC, so that's carbon SMC, right?
Yeah.
According to the flow and therefore the resulting mechanical properties.
Yeah, so that's really part of this latest project, and what we want to get away from is an assumption that if you have flow, all the fibers align, because we don't think that's true, and we're validating some data at the moment, which we think is going to prove it's not true. That 1D flow doesn't automatically mean you have fully aligned fibers. You still have a distribution of fibers which could be aligned with the flow. And could be aligned in different orientations, and so Thermos still allows you to have that bring that variation into your model and predict your weakest and strongest parts, and so you know your true safety factor for that part, and really teach the designer about how we can improve this part and do it all virtually without the expensive SMC tooling.
Okay, thank you for your question, Juan Pablo. Let's move on then one more time, or take a step back. Now you've talked about testing composites. What is the importance in testing composites? What is your stance on that?
Yeah, well, as we spoke about before, the inherent tunability of composites means that every time you change something, you change something else, and that's through the fiber, as you know, okay, but also through the resin. In composites, a good fiber and a good resin doesn't necessarily make a good composite, because that bond is absolutely critical to their performance. And then you can change things through the processing as well. You can binders and other chemicals you can put in can also change the properties. So for some properties, it's quite stable. If you look at, say, the tensile strength, okay, it's mainly a fiber-dominated property, and it will be quite stable across composites. But when you're looking at complex failures like crash, where you have a number of different failure modes potentially all occurring at roughly the same time, those properties, those damage properties, can be absolutely really sensitive to small changes. And you know, in the crush we showed in the energy absorption, you can go from materials that have, you know, you might find a material with 1/10 the energy absorption of a different material. So we've understood this for a long time. We partnered in the early days of the project with the National Physical Laboratory in the UK, and I think together we grew up our composite testing capabilities, our understanding of composites, and how to measure just things are different. Compression is different in composites than it is in metals. It can be more sensitive. It's a more difficult test. You know, you've got a lot of things that are a challenge. So we built up these capabilities with MPL, and then in maybe around 2015, 2016, we just made the decision to bring all this capability in-house. So we built our own lab downstairs from our analysis team that then has all this capability to measure all of those properties we talk about, not just tension, compression, flexure, shear, but also into the damage properties, crack energy growth, crush energy absorption, and a lot of those properties we can measure at different temperatures. So we can do hot and cold. We do a lot of environmental conditioning depending on where the material is going to be used. So yeah, we have those capabilities in house that are now used not just by our OEM customers, but even the raw material suppliers in terms of composites. So the people making composite materials, they are starting to think that you know, our lab has capabilities that they need, and we can produce material cards for them that they can send to their customers to try and displace competitor materials, and just say to them, look, we've got a new material, plug this into your simulation, and it will show you that you can maybe have a slightly lighter structure or slightly better performing structure, and it becomes a nice, easy way for them to sell their materials.
All right, I was a bit surprised now that we have also some live viewers on YouTube. So welcome to our live viewers also on YouTube, because I'm so much focused on LinkedIn, Tim. I was amazed that we have also viewers on YouTube where we are streaming in parallel. So if it happens that someone, is it called now X, or is it still Twitter? So we are streaming also on X, Twitter right now, and on Twitch. If you guys are watching, then also a warm welcome from our side. And anyone who has joined in us later, we are coming slowly actually to an end. But don't worry, we got you covered. As soon as we stop here our live stream, you can watch it anytime you want, from wherever you want. It will be on our on my profile. It is also on my YouTube channel, and soon, as I said, this episode will be also available as a podcast on our Composites Launch LinkedIn group, where I invite you all cordially, because it's free, it's online, and we are the sole composite fiber reinforced polymers community in LinkedIn. Right. So, Tim, there's a lot of meat to what you have said today, and we could go on and on and on. But we would need to conclude slowly our live stream here, because we have called this out for 60 minutes, and we will stay within that range to respect the time of our viewers. Now, the last, of course, obligatory question is sustainability. Now, everyone in the composite industry knows that car manufacturers want to go and are required to, set up their supply chain in a circular way. So we are talking about circular economy, we are talking about recycling. How does you, and have you as Engenuity jumped onto this road? Are you helping your customers to become circular or more sustainable? What is the latest stand you have?
Yeah, so first thing to say, I guess, is that a lot of what we talked about today is helping sustainability. So we can use less material, if we can make lighter products, that's really our aim as a company. That helps sustainability. You make fewer prototypes, that's also helping sustainability. But I guess in a more direct action is some of the work we're doing on materials. And so there are a number of different composite materials out there that are more sustainable than virgin carbon fiber and thermoset, which has been, I guess, the dominant partner in our projects for the last 30 years. And we've started to work in those and look at them in different areas. So things like thermoplastics, how do they behave under these different load cases, not just tension compression, how do they act in damage, how do they act in crash? Also, natural fiber composites like flax. So we've been testing those. We've got some results. So they are a bit of a niche material, but they have some certain purposes that they can have, and you'll only really understand and be able to design to the maximum capacity of that material if you test it and understand it. And lastly, recycled carbon fiber. There's a few areas there. One, we're testing some recycled carbon fibers to see how they behave and their strength properties and how they can be used in different applications. But also a lot of recycled carbon fiber comes out as short fiber, randomized. If we're looking at, again, thin, lightweight structures, it's a good compatibility there with the Therma software. And if you see that variation, then it might be a contender to analyze it with Therma rather than another technique. In terms of our projects, we're working on a number of new sustainable technologies, as I guess a lot of people are in composites, in terms of contributing to sustainable vehicles. So in the hydrogen arena, we're doing a lot of development of hydrogen tanks, trying to select the best materials there. And there's a lot of people doing analysis of hydrogen tanks only really look at the fibers because it is a tension-dominated property. But there's also a lot of research going on in resins, and so we're trying to use virtual development to help with resin selection. Should we be using cheap resins, something that just holds the fiber together, or should we be filling them with tougheners? Does that provide you with value, longer life, less carbon fiber, that sort of thing? So that's research we're leading in hydrogen. And in electric vehicles, we're working on things like battery enclosures. That they're absolutely critical that in a battery enclosure you don't crush the battery, you don't cause any fires that way. And so all our crash analysis can help companies there. And again, through virtual development, your crash enclosures could probably be lighter, just as safe, but lighter. We've optimized material, optimized layups, for example.
Okay, wonderful. Thanks, Tim. That's a great outlook with the sustainability activities you are doing. And of course, composites, because of its longevity, is a sustainable concept in itself. And you can also, drive this further on the sustainability side. So this is it actually from my side, Tim. Anything you want to add from your side? What's the next thing your viewers should do right now after they have finished this live stream here? What's your call to action?
Yeah, I just say to all our viewers that we're a very friendly bunch, and we're happy just to discuss with people their projects at an early stage if they're considering developing a new product, or they're working on a challenge and they don't quite know how they're going to solve it. Come and have a chat, and we can talk to you about your processes. It doesn't, there's no requirement to work with us in the future, but I think that through working in a number of different industries and on a number of different products, we probably have some insight that people haven't seen yet, and could just help improve that product development and make it slightly more efficient, faster, and better chance to succeed in the future.
Yes. And finally, I would like to add the way going forward. I will meet Engenuity, Tim Hall, and his team on the International Composites Summit in Milton Keynes that takes place on the 6th and 7th of September. So if by any chance you are in Milton Keynes, have a look at and visit the booth of Engenuity at the International Composites Summit. I will be there also. If you are there by any chance, let's have a chat. If you want, we can have an interview like this. I will interview for sure the Engenuity team. And on the day after, on the 8th of September, I will be in Burgess Hill and visiting the team on site. So stay tuned. We will fill you in with more material, with many more visuals from their sites, from their site, and also from their computers. So stay tuned. Thanks for joining us to this LinkedIn live stream, which you can obviously watch on YouTube and also listen as a podcast. Thank you so much. Thanks, Tim, for your time and for your insights.
Thanks a lot. Okay.
Bye-bye.